All right, welcome everyone. Welcome to the first session of the day. This is a session with full papers, so this means 18 minutes for the presentation. Then I'll start playing the music and someone will walk you off the stage if you overuse your time. I mean, I'll just signal you basically at 1 minute or 2 minutes before that limit. The first presentation happens to be also the one that received the Best Paper Award yesterday. So those of you, I mean, you can clap. You won't clap now a priori. I give him a warm welcome. Who wishing? Was this Dennis that wishing? So Matthias, he's a PhD student closing the end of his PhD student career at TU. It sounded a little dramatic, but yeah, at TU Darmstadt. He's interested in physical layer security and reverse engineering of firmware for wireless communications. And I had a chance to interact with him last year because he was instrumental in organizing the WiSec that took place in Darmstadt. So, floor is yours.
So, thanks, Panos, for the introduction, and ladies and gentlemen, welcome to today's talk. It's about implementing a reactive jammer on an off-the-shelf device, in this case, a simple smartphone. So let me start with a little motivation. So, first question that comes up is, what is a reactive jammer? I think most of you may know. So, in the end, it's assume that two devices are communicating with each other. They are exchanging frames, sending back acknowledgements whenever a frame is received correctly. So assume for whatever reason you want to avoid that those two devices can communicate with each other. So one thing to do is to simply get your large military equipment, park it in front of your house, and whenever you transmit a frame, the jammer will send out a jamming signal to destroy the frame from being received correctly. Unfortunately, it's very easy to spot such devices in your garden, for example. So our intention was to replace them with simple smartphones. In the end, achieving the same goal, whenever a frame is transmitted, we analyze it, and if we want to target it, we just jam it. So next question is, how did we implement this kind of jammer on a smartphone? And to understand this, we will have to take a closer look into the internals of a Wi-Fi chip running in such a smartphone. In the end, they are all full MAC chips. That means besides the physical layer and a real-time processor, they also contain an embedded ARM processor to do all the non-time critical MAC layer processing. Now, if we want to implement the jammer, we cannot do this in this ARM processor, but instead we have to go to the real-time processor. Why is this the case? So let's look how frames are received. So whenever a frame is received, it is an analog waveform transmitted over the air. It will be received by the physical layer, and this one converts it into a sequence of bytes. And the real-time processor can analyze this sequence of bytes in real time. And then you can say, we are waiting for a certain sequence of bytes to occur, like a MAC address or a UDP port, and then we trigger the transmission of a jamming signal. And this is all done in this real-time processor. So if you attended, I think, the WiSec 2014, there was already a solution that did something similar on routers. So it's based on some prior work in the end. However, using smartphones first makes it mobile, and on the other hand, it also makes it a little bit more difficult because now we have to cope with those full MAC Wi-Fi chips, while on the routers you only had to cope with soft MAC Wi-Fi chips, which didn't include such embedded ARM processors. So what makes it so hard to cope with those full MAC chips? In the end, you can think about it as an in-jailed chip with a proprietary real-time and a proprietary embedded ARM firmware. However, to be able to somehow jailbreak the Wi-Fi chip, we developed the Nexus framework, also presented at last year's WiSec as a demo. It allows you to write patches for the Wi-Fi firmware in C so that you can simply patch it, and it also allows you to change what the real-time processor does. It's all open source, so if you want to try it out, simply try it out. So next thing is, what kind of jamming signals are normally transmitted by jammers. So let us first look at how the signals of normal Wi-Fi frames look like on the physical layer. So assuming an OFDM system, which is most common today, you are transmitting your frame over multiple subcarriers distributed over the frequency band in which you transmit. The frame will go through a wireless channel and thereby be disturbed, so amplitudes and phases change on a per subcarrier basis. And the receiver somehow has to cope with this and revert the effect of the channel to get out the original data. So how does the implementation on the router work in the end? So whenever they receive a Wi-Fi frame that they want to jam, they simply start transmitting another Wi-Fi frame. But this has a certain downside, because assume that your transmission power is normally limited in such a system, for example, to 100 milliwatts. So if you transmit a whole Wi-Fi frame, the 100 milliwatts are distributed over all of your subcarriers. So in each of the subcarriers, you only have a very low energy. So another solution to this is generally developed on software-defined radios, because there you have the ability to design arbitrary waveforms that you want to transmit, which makes it easier, for example, to implement a pilot tone jammer. So you can simply focus your 100 milliwatt you have for a transmission to only 4 pilot tones in your Wi-Fi signal. And the pilot tones are very essential to be able to somehow invert the effects of the channel at the receiver. And therefore, by jamming only those pilot tones, you can very much disable the correct reception of the frames. So now our intention was to actually bring this feature of the software-defined radios also to our jammer on smartphones, to somehow enable some software-defined radio abilities on the smartphones. So to figure out how to do this, we had to dig a little deeper into the firmware and what it does. Unfortunately, there's no source code of the firmware that is freely available, and also the firmware is just a binary blob, so it doesn't contain any symbols to find out where different functions are. However, the firmware running on the full Mac processor is actually containing similar functions as drivers used for soft Mac Wi-Fi cards. Such Broadcom SoftMac Wi-Fi cards, for example, are used in MacBooks. And what we did to analyze the functionality that should be in the full Mac chip is to actually look into the proprietary Wi-Fi driver running on the MacBook. And the nice thing here is, as you can see down here in this IDA window, you actually get symbol names for all the functions that are included in this driver. And by scrolling through the list of functions, we found one function that is called WLC phi TX tone. And that made us think, so if there is a function inside this driver that can let you make transmitted tone, maybe it's also possible to transmit other signals with your Wi-Fi card. Yeah. You may ask, why do they have such a function? It's just for internal calibration reasons. But we managed to actually transmit data using it. So to see how this function works, we have to take a closer look into the physical layer. And the physical layer actually consists of some baseband implementations. So depending on your Wi-Fi standard, you have the OFDM modulation or DSSS implemented there. And after generating your actual waveforms in the digital domain, you pass them to the transmitter. They are converted into analog signals, up-converted to the transmission frequency, and then amplified and transmitted. And on the receiver side, it's just the other way around. So if we use our WLC phi TX tone function, we actually use, or we observe that an additional component in the base layer is used, which is called the sample play buffer. The sample play buffer allows to actually store samples that represent the waveform of a signal that should be transmitted. Think about it like a wave file for audio files, which just also stores the waveform of your audio signal. So those samples are normally called IQ samples, and they can be generated in the embedded ARM processor, put into the sample play buffer, and then we can send a run command to the sample play buffer to play back those samples. They are passed to the transmitter, which actually results in a transmission of a signal. And therefore, we are able to transmit arbitrary signals with the off-the-shelf Wi-Fi chip. So let me compare the different solutions that we have here. So using the smartphones, we gain mobility. So we have our first mobile jammer, and we also embed the ability to transmit arbitrary waveforms into an off-the-shelf device. So let me continue with some experiments we did to evaluate the system. A very simple experiment just to see if the jammer is working correctly is to have two nodes. One is transmitting Wi-Fi frames, the other one is receiving them, counting correct frames and sending back acknowledgements if they were correct. Now what we do with the jammer is whenever the transmitter transmits a frame, we start jamming this frame. But of course, up to the point where we want to trigger the jamming, the headers will still be correct in this Wi-Fi frame. So our receiver can actually detect if there was an incorrectly received frame received, and thereby count it as a jammed frame. Sometimes it can also happen that our jammer misses to jam a frame, either because it didn't correctly receive the frame to be able to analyze it, or because the jamming energy wasn't sufficient to jam it at the receiver. So yeah, in our experiments, we vary different parameters. For example, for the jammer, we varied the transmission power for the jamming signal, and on the transmitter, we varied the modulation and coding scheme. And some other parameters, but I don't show all of them here in the presentation. So let me look at the results. We have some bar graphs here. So for different modulation coding schemes, what you can first observe is the first bar always indicates how many frames were received correctly if the jammer was deactivated. And you can see that we only receive correct frames here. And then internally in the Broadcom chips, to actually increase the transmission power, you have to decrease the so-called transmit power index. So it's just, yeah, the inverse, which is somehow a bit weird, but okay, it's how they implement it in the Broadcom chip. So as you can see, with the highest transmission power, we can successfully jam all frames at those modulation coding schemes. And if we decrease the power, we will also jam less frames correctly. Which is somehow a result that we would expect from the jammer if it works correctly. So the next experiments we did was to somehow figure out the selectivity, because it should be reactive and only jam the frames that are intended to jam. So we did an experiment with two transmitters. And with those two transmitters, we intend that one transmitter can transmit frames without being jammed. Okay, without the jammer, the other one can also transmit. But as soon as we start our jammer, we tell it to only jam the frames of transmitter 1, but not the frames coming from transmitter 2. So, and if we look at the results of those experiments, we can see that this is actually the throughput of a UDP transmission. If only node 1 or only node 2 is transmitting, they get both a high throughput. If both are transmitting at the same time without a jammer, they have to share the bandwidth of the channel, of course, and therefore they only get half the throughput. But as soon as we start our reactive jammer, we can see that the frames of node 1 are jammed very efficiently. It also means that node 1 goes into retransmissions and uses a backoff between the different retransmissions, so it transmits very seldomly. And so there's more capacity for the second node to transmit frames. So the next thing is, we thought if we can transmit with two nodes, it's just a very simple scenario to just jam one node. But what we wanted to do is, or to figure out what happens if one node is actually sending frames on two different UDP ports, for example, because it's running two different services. And our intention was to only jam one of the two services running on this one phone. And you can think about a scenario where you have a mesh network and there's a vulnerable service that could be attacked by some attackers. And you just want to jam this one service, but the other one should still go on because it's an emergency service or whatever. But what we observed is whenever we run our jammer, so the first port is not jammed, of course, but if we transmit frames on the second port, they will be jammed. And of course, what is happening after you transmit a frame, you're normally waiting to get an acknowledgement back. And if you don't get it back and the timer runs out, you will somehow schedule a retransmission. So you're scheduling a retransmission that has to be jammed again. Now, if we have two different nodes that we want to jam, that is not a problem. However, if on this same node we actually want to transmit some data on another port, we cannot do this because the internal state machine in the MAC layer is still handling those retransmissions. So how do we cope with this problem to be able to continue transmitting the frames on the other port that we want to let go through, while jamming those on the port we intend to jam? Therefore, we thought, yeah, it might be the simplest solution to simply trick the transmitter in thinking that the frame was received correctly. So if we jam a frame, we simply forge an acknowledgement and send it back to the transmitter, and so it can continue to transmit on the other ports. Here you can see it in the time domain, how it looks like when you run an oscilloscope or spectrum analyzer in the time domain. You can see this one is actually the Wi-Fi frame that was transmitted. This is the jamming signal here, and this is the acknowledgement forged by our jammer. So, and by doing this, the transmitter can go on to transmit on the other port. If you look at the results, you can see it here with no jammer. Both of them have to share the spectrum in the end and have half the throughput. If we only run the reactive jammer, you can see that most of the frames of port 22 are jammed, and there are a lot of retransmissions that are also jammed, and the transmissions on the other port do not really come through. However, if you use your acknowledging jammer, they still have to share the bandwidth. All of the frames on one port are jammed, but the others can still go through, which is somehow an advantage in certain scenarios. So now the question is, if we have to jam more frames, we might use more energy. So we did some energy analysis by connecting a power analyzer to the battery ports of the phone and analyzing how much power is drawn by the whole phone if we run our jammers. And you can see if we run the reactive jammer, it takes you less than 300 milliwatts, which means like more than 30 hours of operation. However, if we run the acknowledging jammer, it's a power drawn like 700 milliwatts, which means we can only run the jammer for like 12 hours. So to cope with this problem, we thought, what could we improve here to be able to jam with less power? Because sometimes you're jamming with a certain power, but you do not even need that much power to destroy the frame at the intended receiver. Therefore, we developed a very simple adaptive power control algorithm as a state machine in the real-time processor. It has 3 different states it can be in. The first state is the learning state. In this state, we simply jam each frame that we receive and that we want to jam, and then we count the amount of acknowledgements coming from the intended receiver. And if this amount of acknowledgements is higher than a certain threshold, we simply improve our jamming power. So if the amount of acknowledgements is lower than the certain threshold, then we go into our next stage, which is the jam X stage, where we run our acknowledging jammer. So whenever we receive a frame, we jam it, and then we send back an acknowledgement. But during this phase, of course, we are blind because we cannot see if the actual receiver received the frame correctly. So after a certain number of frames, we jam in this state. We go to the next state, which is the check state. In this one, we again disable the acknowledgements, but only jam frames and count how many acknowledgements we received. And depending on how many we received, we either increase or decrease the jamming power or go back into the learning state as a fallback option. So that all comes with a cost, because by reducing the power, it can be that some of the frames that we intended to jam can now go through until we increase the power again. But in the end, we use less power overall, so I think we can run the jammer like 19 hours long. So if you're interested in this stuff and want to try it out on your own, I brought 4 phones with me, and tomorrow in the demo session you can play with it. On 2 phones you can run transmitters, on 1 you can run the jammer, design your own jamming signal in an equalizer-like fashion, and on the receiver you see some bar graphs to see how many frames were jammed or received correctly. So thanks for listening, and if you have any questions, feel free to ask.
Yes, Carl.
How much of this can you do in the face of encryption at various levels? Like, for example, if all 3 nodes run WPA2 or something like that?
Yeah, so I mean, if you are activating encryption, you cannot see the UDP port you want to jam, which we did, but you can still jam according to the MAC address, for example. Or you can say, you can also jam on some of the physical layer settings to say, I want to only jam frames with a certain modulation coding scheme. So you do not even care about the content of the frame. That you could use for some kind of a downgrading attack to only use certain modulation coding schemes or something like this.
So maybe I missed the first couple of slides, but what is the motivation? Would you like to basically be able to block certain communication?
I mean, the main motivation is to show that it is actually possible to implement such jammer on a smartphone. And you can use it for different applications, like either for malicious applications or for some friendly jamming applications. Think about a firewall, for example, in a company where you have a mesh network, there are vulnerable services, and you want to be able to jam those. We also have another example. For example, normally in the 2.4 gigahertz band, you are not allowed to transmit on 80 megahertz channels. With our Nexus framework, you can still do this. So what we try to do is, can our jammer also jam those rogue transmissions in the 2.4 gigahertz band? And we realized that it can.
Okay, but I mean, jamming the packet and jamming the communication are different. So would you be able to guarantee that no packets will be able to pass?
No, you can't, because first of all, the reactive jammer has to receive the frame correctly, at least up to the point where you want to check the bytes that allow you to trigger the jamming. If this one didn't work, because you are too far away from the transmitter, for example, you wouldn't be able to jam the frames, of course.
Yeah, and even adaptive control might also prevent you because, right, it's difficult to estimate what is the correct power because you need to estimate it on the receiver side. And of course, your channel to receiver as a jammer is different from the sender to receiver.
That is true, but therefore we have this adaptive power control jammer that is actually checking for acknowledgements coming from the intended receiver. So if no acknowledgements are coming from the receiver, you can assume, as long as you can assume that it will always send an acknowledgement, that the frames are either correctly received or not. So.
Sometimes it's difficult to interpret the loss, right? It can be.
Yeah.
Anyway, we can take it offline. Thanks a lot.
Excellent. So, I don't think I need the microphone, but in the interest of time, after this Wimbledon style exchange with Ivan and Matthias, shall we move to the next talk? And then, of course, the general chair, I can mistake him. Anyways, let's give another round of applause to Matthias and then